Hello students, welcome to YouTube channel of Pravegaa Education. So I am solving questions from David J. Griffiths Electrodynamics, and this is a very nice question that I am going to discuss. Just see this question. Two long coaxial cylindrical metal tubes, inner radius A and outer radius B, stand vertically in a tank of dielectric oil having susceptibility chi E and mass density rho. The inner one is maintained at potential V and the outer one is grounded. That means the potential difference between inner and outer surface is capital V. To what height h does the oil rise in the space between the tubes? So students, this is question where the dielectric is sucked into vacuum by force, and that force is given by, you remember, the energy of a capacitor is half CV square. Okay, so I am just giving you a sense of it. The real derivation is little complicated. So the force will be just derivative of this. It will be half V square dc by dH in this case, because the oil will be sucked into the low dielectric medium and it will start rising, but then because of its weight, because of the gravitational force, both will achieve an equilibrium, and that will be the final height h up to which the oil will rise. So actually this is the question. You can clearly see that I need the capacitance, and once I get the capacitance, I can differentiate it with respect to h to get the dc by dh, and then simply half V square. Okay, so here we have vacuum and here we have oil, and there is a potential difference between this and this given by capital V. So what I will do, I will just consider it as a thin rod because I want potential difference between this and this point, and I want to write electric field also for some purpose. We will see that. So I will take a linear charge density here as lambda, and in the oil, because we have a different dielectric medium, let us take the charge density at lambda dash. So you know, at a point P, suppose this is the point P, if I write the electric field just above the interface and just below the interface, both electric field will be parallel to each other. So I will write the electric field, which is lambda by 2 pi epsilon naught r in the vacuum, and because both electric field are parallel to the interface and parallel component of electric field is continuous, so it will become lambda dash by 2 pi epsilon r. Epsilon, I am taking permittivity of the oil. Okay, so in this way I will get a relation 2 pi cancel, r cancel, lambda dash will be epsilon by epsilon naught lambda, which is epsilon r lambda. This will be the charge density inside. Okay, so now I want to write the capacitance, and you know Q is equal to Vc. So for capacitance, I need charge by volume. That's why I have written lambda dash and lambda. Okay. So now if I take this total length as L, which is constant, so what will be this length? This length will be L minus H. Okay. So total charge will be, in this case, the total charge will be lambda into L minus H plus lambda dash into H upon V. This will be your capacitance. and now put this in this formula. What you are going to get is F is equal to half V square dC by dH. So differentiate this, you will get 1 by V. Differentiate this, you will get minus lambda plus lambda dash. Correct? Now put the value of lambda dash here, which you have calculated from the parallel component of electric field. So this will become 1V and 1V will cancel, half V and minus lambda plus epsilon r lambda, and this will become half, take V and lambda common, it will become epsilon r minus 1. Now chi e is given. So what is chi e? It is 1 plus epsilon r. Okay, so epsilon, just a second, this epsilon r minus 1 I can write in the form of chi e finally, which is given in the question. Okay, so that I will replace. So 1 plus chi e is equal to epsilon r. 1 plus chi e is equal to epsilon r. So epsilon r minus 1 will become chi e. That I will replace. Okay, so this is my force. This is my force, and this would have been going on and on upward, but because mg will come into the picture, so that's why it will achieve an equilibrium where both forces will balance. The force where the dielectric is taken into the low dielectric medium, and one force is because of the weight, so both will become equal at equilibrium. So let me write that. So this mg, what will be the mass of the oil? It will be given by density into volume. What is volume? Pi h and b square minus a square. Pi r square h is volume of the cylinder, and I want only that much volume which is contained by the oil. So this is mass into g is equal to half V lambda epsilon r minus 1 is chi e. So it will become chi e. Okay. So now what will be the h? And finally we have to write everything in terms of the quantities given in the question itself. So h will become equal to half V lambda chi e upon 2 rho pi b square minus a square. Only one thing is extra which we had taken for our convenience, and that is lambda. So it is so easy to write the potential difference. Let us write it in the vacuum, the potential difference, because we know the profile of electric field. So the potential difference will be lambda by 2 pi epsilon naught ln b by a. This will be the potential difference, because you know V can be calculated by minus integral E dot dr, and when you integrate dr by r will become log. So this is standard result also for cylindrical. So lambda I don't need, I will replace it. It will become half V, lambda will become V into 2 pi epsilon naught upon ln b by a, and here it will become chi e, and here it will become 2 rho pi b square minus a square. Okay, so finally you have to check something will cut also. like pi and pi, 2 and 2 will cut, and this will become V square, and this is your final answer in terms of the quantities that is given. So our oil will try to go upward, but it will be balanced by the weight of the oil, and up to that level it will rise. So this is a very nice question in which concept of the dielectric moving from low dielectric medium to a high dielectric high dielectric medium to low dielectric medium, and you can read further from Griffith for more details. Okay, thank you so much.